like this. So classical applied mathematician in Central Europe, and today he's going to give a talk that bridges very nicely these applications with the theory that is being done in this group, because he's talking about constraint qualifications for optimization problems in Banach spaces. So a little bit of technical finesse there, and it's based on asymptotic KKT conditions because it's difficult to directly, as you probably know when you work in your Asplund spaces and don't want to go beyond, then you see that there are some problems if you want to go beyond. And this is probably what this is exactly about. So let's see what Gerd has to say, and then maybe we can know more.
Okay, thank you, Janosch, for this introduction, also for the invitation to Australia. The first time that I give a talk in Australia. As you can see, it's a joint work here with Patrick Melitz, who is a postdoc with me in Cottbus, and with Christian Kanzow from Würzburg and his PhD student, Eike Birgens. And as already said by Janosch, it's about asymptotic KKT conditions, so which is an extension of the theory of KKT conditions, which was done in finite dimensions in the last 10 years. And we tried to transfer these ideas to infinite dimensions. And in infinite dimensions, you have some different problems than in finite dimensions. And this is what this talk is about. So first, I would like to speak a little bit about infinite dimensional optimization, and in particular on KKT conditions. And then we will focus on these asymptotic KKT conditions. So first of all, I will give the definition, and I will also give a theorem which shows, in a sense, that all local minimizers are actually AKKT points under some fairly mild conditions. And then in the third section, we will speak about this AKKT regularity, which then ensures that the AKKT conditions yield KKT conditions for the point under consideration. In section 4, we relate our new constraint qualifications to classical constraint qualifications. And then I will speak about 2 example problem classes. And in particular here for these equality constraints with constant rank, we can actually improve something new with our AKKT conditions. And finally, I give a short outlook. Okay, so on this slide here, I have the basic problem, which this talk is about. So you should keep in mind this problem here in the entire talk. Maybe you would write it down on a sheet of paper so that you have it in front of you for the entire talk. So I cannot write it here on the blackboard. Okay, what do we have? We have 2 Banach spaces here, x and y. The functions f and capital G are continuously Fréchet differentiable, and here on the right hand side of the constraints, C and K are just some closed convex sets. So we have here two kinds of constraints. We have this let's say easy constraints. X belongs to a convex set C, and here some nonlinear mapping G of X should be in K. So this of course is a non-convex constraint here. But the entire non-convexity, so to speak, is captured by this continuously Fréchet differentiable mapping capital G. Okay, and this constraints X and Z, you can think of it as some easy constraints, and they will also be handled differently in our theory, and we will see it in the AKKT condition. So it makes sense to put some easy constraints here as in the first line, so constraints which, for example, can be handled explicitly by numerical methods, for example, bound constraints or sign constraints. And everything else we can put here in the second type of constraint. And this problem class here generalizes standard nonlinear programs from finite dimensions. And I would also like to mention that this constraint here with the set K can also model equality constraints, because if we take such a product structure, K is equal to the 0 times a different convex set K hat. And then this constraint g of x in K enforces that the first component of G must be exactly 0. So we have an equality constraint there. And then the second part of the constraint can model inequality constraints, as you know from standard nonlinear programs. So yeah, this is quite general. Many problems can be cast in this framework here. Now we need some cones from convex analysis. Yeah, what do we need? We need the radial cone. So for a convex set C and a point in the set, this radial cone consists of all directions in which you can go a little bit in your convex set C. Sometimes it's also called cone of feasible directions. So yeah, these are directions which you can go for a while and you stay in the set C. And the tangent cone is just the closure of this radial cone. And we also need the normal cone. You can write it down in several ways. For example, it's the polar cone of C minus x bar, or it's also the polar cone of the tangent cone. So this for convex sets. And we also need tangent cones for non-convex sets. And here for a non-convex set Q, I have brought to you 2 tangent cones. Actually, there's an entire zoo of tangent cones. We need here, in particular, 2 of them. So in the first line, we have the so-called Lagrangian tangent cone. And these are all directions which can be approximated by directions from the set. So we have here two sequences, xk, tk. xk converges to x bar, and xk should come from the set Q. And tk is a scaling parameter, and we need that this xk minus x bar divided by tk converges to the direction d. Well, this somehow all directions which can be, which are tangent to the set Q in the sense here that it can be approximated by these different quotients when xk goes to x bar. And then we also need at some point the weak tangent cone, weak Lagrangian tangent cone. And the only difference is that we have here weak convergence. So the weak tangent cone might be a little bit larger. And I think at one point we also need the Clark tangent cone, just for a moment in the proof. If you know the Clark tangent cone, then you also know that the Clark tangent cone is smaller than this Lagrangian tangent cone. So here's an entire zoo of tangent cones. But luckily, if we have a convex set, then all these notions coincide. And therefore, it also does not make problems that we use here the same notation for a convex set as here for a non-convex set, because this definition boils down to that one for convex sets. Okay, now we have our basic minimization problem, and we want to obtain some optimality conditions. And what we do is here we denote the feasible set by capital F. This is the set of all feasible points of our problem. And the very basic optimality condition is that minus f prime belongs to the polar of the tangent cone. And here I've written the polar of the tangent cone because capital F is a non-convex set due to the nonlinear mapping G here. And yeah, you can also write down here some kind of normal cone to the set, but for this talk, I want to stick with the polar cone of the Lagrangian tangent cone. And the proof actually is quite easy. If you take a direction from the tangent cone, then you know you have the sequences xk, tk, and in particular, this different quotient xk minus x bar divided by tk converges to d. And I've not written this down here, xk converges to x bar. And because xk converges to x bar, we know that xk belongs to any neighborhood of x bar if k is big enough. And since x bar is a local minimizer, and you get that here this difference must be a non-negative. So because f of xk must be bigger than f of x bar. And then again, if we divide by dk, we have still this inequality, and due to the convergence of this different quotient, one can check that the right-hand side here converges to the directional derivative f prime times d. And therefore, this here is always non-negative for any d from the tangent cone, and this means exactly that minus f prime belongs to the polar cone. Okay, so this is a very basic optimality condition, but what is not so nice about this optimality condition is that it's not easy to describe here this tension cone or its polar cone. So these two cones are not so easy to use, and what we, and in particular, it's not possible in general to describe these cones by the problem data. And therefore, we introduce a different cone, the so-called linearization cone, which can be written down in terms of the problem data. So what we see here in the definition of this linearization cone is just the data from the constraints. We have here Z, we have the derivative G prime, and we have the tension cone to K here. And the idea now is to take the optimality condition from the last slide, replace the tension cone by the linearization cone, and then we had here a polar. We also need the polar of the linearization cone. And if you are in finite dimension, then this is very easy, because the cone which appears here on the right-hand side in finite dimension is just a cone which can be described by finitely many linear equality and inequality constraints. So this is just a polyhedral cone in finite dimensions, and then you can use the lemma of Farkas to compute the polar cone. But in finite dimensions, things are different. In particular, you do not have such an unconditional lemma of Farkas without any further assumptions. And the closest what you can get is the following generalization of the lemma of Farkas. To say something about the history, I think this theorem first appeared in the paper by Curtius from 76. And actually, the proof therein contains a very small error which can be fixed by the theorem of Krein-Schmuljan. Actually, in the proof, he used a weak star convergent net, so not a sequence, a net. Is there any question? Sorry, I don't understand. What? Is there any question? Okay, so I just continue. So in the proof, he used a weak star convergent net, and then at some points he said the weak star convergent net is bounded, but actually this is not the case. So it is true for weak star convergent sequences, but not for nets. And this you can fix by the theorem of Krein-Schmuljan. And actually a correct proof, for example, you can find in the book by Shirocek. And you see here we need some additional assumption. We need that this set here on the left-hand side coincides with the entire space Y. So somehow some kind of surjectivity assumption. And then you can compute the polar cone of the linearization cone by the set on the right-hand side. And there, maybe one should also mention, it's also this conclusion also holds under a slightly weaker assumption. It is sufficient to assume that the set which appears here on the right-hand side, that this set is weak star closed. So closed in the weak star topology, and then you can also prove this formula here. And okay, and what we can also say about this formula is it's also possible to prove this formula by the sum rule for convex subdifferentials, and then this condition here comes from the Attush-Prezis condition for the sum rule, sum and chain rule. And why can we apply the sum rule for convex subdifferentials? There you have to recall that the normal cone here we have the normal cone to a convex set. You know that the normal cone of a convex set can be interpreted as the subdifferential of the indicator function. And this is the key. This observation is the key here to apply the sum rule for convex subdifferentials. Okay, and a different proof of this theorem can be done by using the open mapping theorem, which is shown in the paper by Curtius. So it's just a extension or generalization of the standard open mapping theorem from functional analysis. This can also be used to prove this result here. Okay, so what does this mean here? If we can now replace the tension cone by the linearization cone in our optimality conditions, then we end up with the polar of the linearization cone. And then you can use the theorem here to get optimality conditions in a quite nice form, namely as KKT conditions. Okay, and what remains is to replace the tangent cone by the linearization cone. And one result which allows this is a theorem by Robinson, which for multifunctions, which holds under an interior point assumption. So you need that 0 is an interior point of the set, which is here in the parenthesis. And then you obtain this equality here, that the tangent cone coincides with the linearization cone. And now we can put everything together, which was done in the paper by Zove and Kotzius from 76. And they have shown, first of all, that this condition by Robinson can be written in this way. So again, it's a kind of surjectivity assumption, and it's almost the same assumption we have seen on the previous slide. On the previous slide, you have seen this assumption with tangent cones here, and now we need the same assumption with radial cones here for the set C and for the set K. The radial cone is a little bit smaller, though this assumption is a little bit stronger. And actually, there are examples which show that if you put here tangent cones, then the conclusion is no longer true. And then, if this assumption is satisfied, and if you have a local minimizers, then you get the KKT conditions, which means you have a multiplier from the normal cone of K and a multiplier from the normal cone of C, such that the derivative of the Lagrangian is 0. And this means that you have here f prime plus the adjoint of g prime times lambda plus mu is equal to 0. So or speaking differently, you can write f prime as the negative of this combination here. And these are the KKT conditions in infinite dimensions. And you see we need some constraint qualification, in particular what people in optimal control, for example, typically use is this optimality condition from Zove and Kotzius, because this is somehow the weakest and easiest to use optimality condition in infinite dimension, which is available. And I should also say that if you apply this optimality condition for standard nonlinear programs in finite dimensions, what you get is exactly the Mangasarian-Fromowitz constraint qualification. And you also know that in finite dimensions, there are a lot of constraint qualifications which are weaker than the Mangasarian-Fromowitz constraint qualification. There's much research about this, in particular some constant rank constraint qualifications, but similar things are not available in infinite dimensions, because it's also quite hard to say in infinite dimensions what does it mean that a certain mapping has a constant rank. Or these constant rank constraint qualification also typically use index sets of your inequality constraints. This is also not available in infinite dimensions. So this is somehow the easiest to use and weakest constraint qualification which is available in infinite dimensions in order to get the KKT conditions. Okay, and now we can go a step further towards the asymptotic KKT conditions. Okay, here first of all I recall the KKT conditions, and I had also said that this implication which one is interested in, that local minimizers are KKT points, need some constraint qualifications. And this Zove-Kotzius constraint qualification is quite strong because it resembles the Mangasarian-Fromowitz constraint qualification from finite dimensions. And now what we do with our asymptotic KKT condition is we take somehow a limiting version of this constraint qualification. And here we use the following definition, which is basically from the PhD thesis from Daniel Steck, which was a PhD student with Christian Canzo. And he used the following definition for an SAKKT point. Here S stays for strong, so we have some strong convergence here. You also have a weak version with weak convergence on the next slide. So what do we have here? We now no longer have single multipliers, but an entire sequence of multipliers, and also a sequence of points xk. And xk is now not points from the feasible set, but xk only belongs to this easy constraint set C. And similarly, the multipliers mu k belong to the normal cone at xk. So here again, we think of that the easy constraints can be satisfied explicitly. Lambda k just comes from the dual space. And what we require here in the end is the following limiting version of the KKT conditions. Xk converges to x bar. Then the Lagrangian is not equal to 0, but just converges to 0, so the derivative of the Lagrangian. And then for lambda k, we have this limiting version of the normal cone inclusion, namely that this duality is smaller than rk for all points y from the set k. And this can be thought of a limiting version of the normal cone inclusion here, because if you pass to the limit formally here, then you have lambda times y minus g of x bar is smaller than 0 for all y and k, and this exactly means that lambda belongs to the normal cone. Okay, so this is just, so to speak, a limiting version of being a KKT point. Okay, and here again, this is the very same definition. I would just give some remarks, some further remarks. So I already said that in finite dimension there's some recent development on some asymptotic KKT condition in the last 10 years mainly by these people here. I already said that the easy conditions are handled explicitly, namely that xk belongs to the set C and mu k to the corresponding normal cone. And this is also motivated, let's say, by algorithms. If you use a numerical algorithm to compute a feasible points, then you have some constraints which can be handled explicitly, for example, bound constraints. And then you get always points which satisfies these easy constraints, and also you get corresponding multipliers. And now it's also interesting to see if we would have convergence of the multipliers. So recall that in these definitions, we do not assume any convergence of the multipliers itself. Yeah, we have the sequence of multipliers. We only require that it belongs to the normal cone in this limiting sense here. And for mu k, we do not have any condition here besides this normal cone inclusion. And if we would have convergence of multiplier, then we would get a KKT point. Because here we have convergence. Here on the left-hand side, everything converges. As I already said on the last slide, we would end up with that the limit of the lambda k belongs to the normal cone at x bar. And here on the left-hand side, everything is continuous. And we could pass to the limit and obtain that in the limit, the derivative of the Lagrangian is exactly 0. But we do not have any convergence of the multipliers here. And it also is interesting to know that the boundedness of the multipliers would be enough, because if both multipliers are bounded, then we can extract weak star convergent subsequences or subnets. And then we have weak star convergence here of the multipliers, and weak star convergence is enough to pass to a limit here in this relation and in this relation. So boundedness of multipliers would also be enough to imply that the point x bar is a KKT point. But these sequences here might be unbounded. And then I already said there's also a definition of a W a KKT point. Here W stays for weak. And there you require here only weak convergence for the points and weak star convergence for the derivative of the Lagrangian. And this is in particular useful for numerical methods, because numerical methods typically produce only weakly convergent sequences here. And I will not speak about numerical methods here, but if you're interested in this stuff, you can look in our paper. And there we have stated a little bit about SQP methods. And typically SQP methods in infinite dimensions produce sequences which satisfy these two properties here. Okay, so but for the remainder of the talk, I think it's enough to think about these SAKKT points with strong convergence here. Okay, and then what's the point of AKKT conditions? Yeah, the point is that we have this theorem here from our paper, which ensures under fairly mild assumptions that every local minimizer is an SAKKT point. And this is different to KKT conditions. You know, I already said this. For KKT conditions, we need some strong conditions to get that every local minimizer is an KKT point. Okay, what do we need here? We need reflexivity of the space X. We need a weakly sequentially lower semi-continuous function here. Both conditions are not too restrictive. And we need a further assumption here, the assumption with the star. This will also pop up at several points in the talk. And this is somehow a assumption on the constraint. And what we need is that if we have a sequence which converges weakly and where the distance of g of xk to the zk goes to 0, then we need that the limit here belongs to the g of x belongs to k. And in particular, this assumption it's rather mild. For example, yeah, if it would be sufficient to have strong convergence here, then this is automatically satisfied because the mapping G is continuous, and then you can just pass through the limit here in this equation, and we get that one. But we only have weak convergence here. So for example, it's enough that G maps weakly convergent sequences to weakly convergent sequences. Then you also get this assumption here. So it's not a very strong assumption. And the idea of the proof is, first of all, we use Ekeland's variational principle. We get a minimizer of this objective function here, where the last term, again, depends on xk due to Ekeland's principle. And now we can use this minimality of xk for this problem and the local optimality of x bar to draw some consequences. So first of all, from this thing here, we have here a further restriction. We have here a ball around x bar, and this means xk is bounded. And then we get a weak convergence of a subsequence of xk due to the reflexivity. We can test here this optimality with x bar. We get that this distance here with xk goes to 0. Then we can apply our equation star. We get that the limit point x hat belongs to this pre-image here. And then we can plug, and then we know this x hat is feasible. We can plug it into the original problem. And this then, after some computations, yield that x hat is exactly our x bar. Then we can raise this weak convergence to strong convergence. And finally, we need some optimality conditions at xk to get our asymptotic conditions for x bar. And this can be done by using optimality conditions for this problem here. And here we can use Clark's calculus to get optimality conditions for this problem. And this, if you write everything down, yields AKKT conditions for our limiting point x bar, so for our local minimizer. So we see here this theorem ensures that under some rather mild assumptions, the limiting point is already a strong AKKT point. And now at the end of this section, I have two examples. The first example shows that the AKKT conditions are really weaker than the KKT conditions. So what do we have here? Our optimization space, capital X, is now split into two parts. So we have a real optimization variable and an optimization variable from the function space L2. This I will call always U is the function alpha is the scalar. U is constrained to be between -1 and 1. So we have some bound constraints on the variable U. And K is just a 0 set. So we have an equality constraint that U is equal to alpha times Q. And Q is a fixed function, which is unbounded. So Q is an unbounded function. This means if you take here an alpha, which is not 0, then also U is unbounded. and then these constraints here on U are violated, because this Q is unbounded. And therefore, the only feasible point is alpha equal to 0 and U equal to 0. So it's just a very boring problem. So the feasible set is only the 0. Then the normal cone to F, of course, is just the entire dual space. But the set here, which appears in the KKT conditions, is not the entire space. So it's a linear subspace of codimension 1. And then it's easy to check that there are linear continuous functions F such that 0 is not a KKT point of our optimization problem, although 0, of course, is the only feasible point. And one can also check that 0 is always an SAKKT point due to our previous theorem. So here there's an example which shows that AKKT points are really weaker than KKT points. And the second example is an example for which also our AKKT conditions fail. But here the reason is that our specs X is not reflexive. So X is here the sequence space L1. And again, we have a very boring constraint, namely G of X, which is X, should be 0. So the constraint is X is equal to 0. So X, again, is the only feasible point. But the caveat here is that the space Y is now L2. So this G here is actually not an identity, but the embedding from L1 to L2. And therefore, one can check after some computation that 0 is not even an SAKKT point, because otherwise it would lead to some contradiction here. Okay. So, and this means that the reflexivity assumption of our theorem is really important here. Okay, now about AKKT regularity. So our goal now is to prove that every AKKT point is also a KKT point, and such conditions we will call AKKT regularity conditions. So which yield that AKKT points or SAKKT points are KKT points. And this motivated, but we also have seen in this theorem that every local minimizer is such an AKKT point. Okay, and for this, I just have given here again the definition of AKKT points, of the asymptotic KKT points. And the idea is now to capture the structure of the AKKT conditions here in a set-valued mapping. And this is a set-valued mapping capital M, which is somehow, which depends on the point X and on this real parameter R. And this essentially captures everything in the AKKT conditions, which is not a limiting condition. You have here this combination of the multipliers. We have here this condition on the multiplier lambda, and mu is from the normal cone. And with this cone, we can get, after a very short computation, that being a KKT point is equivalent to this condition on the right-hand side, that minus f prime belongs to this set M with x bar and 0, because this just boils down to that one, which gives the KKT conditions. And one can also check that the polar cone here of the linearization cone is again this capital M if a weak constraint qualification is satisfied. For example, if this set which appears here, which is that one here, if this set is weak star closed. Okay, this we will need in a moment. Okay, now we have captured everything from the asymptotic KKT conditions up to the limiting processes here. And this is now captured in a Panlev-Koratowski type outer or upper limit. So what we need here is a limit superior of the set M of x and r, when x goes to x bar and r goes to 0. And this defined as follows. So we have a sequence xk and a sequence rk. Xk converges to x bar, rk converges to 0. And we have a sequence vk. Vk must belong to the set M of xk rk, and vk should converge to x bar. And this is the set of all these v bars which can be obtained in such a manner. Just a upper limit of this z-valued mapping. And actually, this is not the only thing we need. Actually, we have here two types of convergences. I hope you can see the color. So I have colored here the convergence of X in red, and here the lim sub in green, because the lim sub means that we have strong convergence here for the VKs. And now we have two other versions where we here still have strong convergence for the X variable, but now weak star convergence for the V variable. So it's the only difference here, the colored bits. And then we have a third version where also the convergence for X is weak. So we have here weak convergence. Actually, there's a fourth combination that we have here weak and here strong convergence, but it is not needed in the sequel. So we have these limit objects, and now we can write down or we can check the definition of being an AKKT point here. An A is missing, sorry. One can check that being an AKKT point, an SAKKT point, means that minus f prime belongs to this outer limit on the right-hand side. And if you now recall that the KKT conditions mean that we have here m of x bar and 0, this now also yields a regularity condition. Namely, we just require that this outer limit is equal to m of x bar and 0. And this is now our regularity condition. If we have this inclusion here for the strong outer limit, then we call the point SAKKT regular. If we have here strong and here weak star convergence, we call it SWAKKT regular. And we have just W regular if we have both types weak convergence. And then from this definition, it's quite easy to check that we have a hierarchy of regularity conditions. So the W regularity is the strongest, and the strong regularity is the weakest. We can also check that if such a subset relation holds, then we have automatically equality, because the right-hand side is always a member here of the left-hand side, a subset of the left-hand side. So instead of subsets here, we can also write equalities, because it's actually the same. And a third remark is that this SWAKKT regularity already yields this polar formula for the limiting cone. And why is this the case? Because we know just by definition that this limit superior here on the left-hand side is weak star closed. And this means that also the right-hand side is weak star closed. And this means we have this polar form. Okay, and now we can just use the definition and plug everything together. If we have an SAKKT point, which is SAKKT regular, then X bar is already a KKT point. And we also have somehow a reverse conclusion. Namely, we can check if we have a point for which this implication holds that every AKKT point is an KKT point independently of the objective function f, then this point must already be AKKT regular. So this means this regularity is the weakest condition which ensures that every AKKT point is a KKT point. And there's also an analog of this theorem for the weak version, which I will not give here in the talk. Okay, and now we can also draw some relations to the classical constraint qualifications. The first I will recall the Robinson-Zove-Kotsios constraint qualification, which holds if we have this surjectivity type assumption here. And I already said the first 2 points I already mentioned. And the third point is also necessary now, or also important in the sequel, because this Robinson-Zove-Kotsios constraint qualification ensures that your multipliers are bounded. And I also said AKKT condition, if the multipliers are bounded, then we get back to the KKT conditions, and somehow we can fit now the pieces together, and we can ensure that under this constraint qualification we have this SW regularity. And the idea of the proof is, first you have to write down everything what you have. So we start with a V bar in this upper limit, and we want to show that this belongs to this set here. And then you just use the definition you have a sequence VK which converges to V bar. VK belongs to this set. You unplug all the definitions, and then at the end you can show that the sequence of multipliers which you have here, the lambda k, mu k, are bounded. And due to this boundedness, you can pass to the limit and you get this thing here. So it's not particularly hard, but you have just to unroll the entire definitions, and then you see at the end that your multipliers are bounded, and this yields this regularity condition here. Okay, now we can also draw a relation to the Asymptotic constraint qualification. So as in finite dimensions, we say that the Asymptotic constraint qualification holds if we can replace the tangent cone by the linearization cone. And we also need here a further condition which ensures that we have the correct polar of the linearization cone. Yeah, and this condition here, you do not see it in finite dimensions because it's automatically satisfied. And again here, also in infinite dimensions, the Asymptotic constraint qualifications imply that all local minimizers are KKT points. And for the next proof, we further need the Fréchet normal cone and the limiting normal cone. And here in the reflexive and separable case, it's particularly easy. Then you can write down the Fréchet normal cone, or this is the definition of the Fréchet normal cone. Due to the reflexivity, we get that this is the polar of the weak tangent cone. And we also have a nice formula for the limiting normal cone, just by this limiting relation here. We take sequences from the Fréchet normal cone, the points converge strong, the multipliers converge weak, and the limit point is then from the limiting normal cone. Okay, and we also need a result which appeared, for example, in the book by Rockefeller-Wetz in the finite dimensional case, but which also holds in the infinite dimensional case. If you have a vector here from this Fréchet normal cone, then you can find a convex and differentiable function for which x bar is a local minimizer, and this v from the Fréchet normal cone is exactly minus h prime of x bar. Okay, and these ingredients can now be used to show the following theorem. Namely, if we have an SW AKKT point, then Asymptotic constraint qualification holds. And the idea of the proof is, in a first step, we show that the limiting normal cone belongs to this set-valued map M of x bar 0. Okay, what do? Is we take a vector from the limiting normal cone. We get these sequences xk, vk. Oh, here some bars are missing. Xk converge strongly, Vk converge weakly from the Fréchet normal cone. And then, because Vk is from the Fréchet normal cone, we get such a function Hk from the previous slide. And for this function Hk, you can show that Xk is an AKKT point, because we have assumed here this condition star. Xk is an AKKT point. You get a sequence of multipliers. For each xk, you get a sequence of multipliers. So we have a sequence of sequences, and now we can one can check that that is possible to pick a diagonal sequence. The diagonal sequence now shows that x bar is an AKKT point, and the regularity now implies that the limit belongs to this set here. Okay, so now these steps here show that the limiting normal cone belongs to this set, and now we can polarize this subset relation. So for the polars, we get the inclusion in the other way around, and now we just to rewrite the left-hand side and the right-hand side. So the left-hand side is just the linearization cone, and this is nice because we would go to Asymptotic constraint qualifications, we need somehow the linearization cone here. Now we have here the polar of the limiting normal cone, and here we can use that the polar of the limiting normal cone is the Clark tangent cone. So I have not introduced it. If you know it, then it's fine. If you not know it, it just appears here once in the proof. So it's the Clark tangent cone, and this is smaller than the tangent cone, and the tangent cone is always contained in the linearization cone. And now we have this chain of equalities here, and this means that the linearization cone is equal to the tangent cone, and this is what the Asymptotic constraint qualification is about. Okay, so we have here that our regularity conditions imply Asymptotic constraint qualification. And now we can also say something about Grignard's constraint qualification. Grignard's constraint qualification now means that the polar of the tangent cone equals the polar of the linearization cone. This is the definition in finite dimensions. In infinite dimensions, it's best to write it in this way. You have here the polar of the weak tangent cone, and here you have this set-valued mapping M at the point x bar in 0. And yeah, one can show, it was done by Gold and Toller, that this constraint qualification is the weakest constraint qualification, which ensures that all local minimizers are KKT points, independently of the objective f. It should be an f here. And then we can also show by similar arguments as for Asymptotic constraint qualification that here the SAKT regularity condition implies a Grignard constraint qualification. And to put everything together, we get the following picture. Here we have our new constraint qualifications, and here we have the following the following implications. In particular, this SW regularity conditions is somewhere between the Zuvio-Curtius constraint qualification and Asymptotic constraint qualification. And yeah, this is the picture of our new constraint qualifications. And the arrows which are labeled here with A and B require some additional assumptions here. Okay, and finally, I would like to speak a little bit about two example problem classes. And the first example is we just look at the problem where we only have equality constraints. So we have no constraints with the C because it's the entire space X. K is just 0, so we have the constraints G of X equal to 0. And in finite dimensions, there is the so-called constant rank constraint qualifications. Namely, you require that the rank of the Jacobian is constant around your point of interest X bar. And now it's a question, this is not really of use in infinite dimensions because there is no notion of rank of a linear map as in finite dimensions. And here, what we can do is we can first take a different or a reformulation of this condition in finite dimensions, because the constantness of the rank is equivalent to the following statement that the norm of the Moore-Penrose inverse is bounded. Yeah, this is just some linear algebra. If the rank goes up, then the Moore-Penrose inverse is somehow unbounded locally. And if the rank stays the same, then this means also that the Moore-Penrose inverse is bounded. And here the easiest example is something like this. We take a matrix A epsilon with 1 and epsilon on the diagonal. Then the Moore-Penrose inverse is this here, 1 and delta, where delta is 0 if epsilon is 0, and epsilon to the minus 1 else. So if you take an epsilon which goes to 0, then the norm of this Moore-Penrose inverse blows up. And this is exactly because this perturbation by epsilon increased the rank of this matrix here. For epsilon equal to 0, their rank is 1. And for epsilon bigger than 0, the rank is 2. And this means that the Moore-Penrose inverse blows up in the neighborhood here. And this condition here now is somehow coordinate independent, and we can reformulate it in infinite dimensions. And there one can use the so-called reduced minimum modulus introduced by Kato in his book on perturbation theory. It's defined in this way here, and this somehow you can think of a generalization of this norm of the Moore-Penrose inverse and to infinite dimensions. I will not go into detail here. It's just a constant which you can associate to every bounded and linear operator. And the main use in the book by Kato, I think, is that you can show that this mapping is closed if and only if this parameter is positive. And in finite dimensions, you can show that this parameter is just the inverse of the norm of the Moore-Penrose inverse. Okay, and now we have the following theorem. We now suppose that this reduced minimum modulus is bounded away from 0 by this beta in the neighborhood of our point. And then we can show our point is AKKT regular. And this is now a constant rank constraint qualification in infinite dimensions. And in particular, this theorem generalizes a recent result by Bloat from 2018. And he also proved a constant rank condition very similar to our condition, but he additionally had the assumption that some subspaces associated with G prime are complemented. And we do not need this assumption here. Our assumption here is slightly weaker. And then a second problem class I would talk about are box constraints in Lebesgue spaces, which are quite typical in optimal control theory. And as Janos said, I also work in optimal control theory. And here box constraints mean that we have just two functions in L2, and our control U is bounded by these constraints. And then you can formulate this constraint set in our abstract framework in the following sense, that you have our G now has two components, UB minus U minus UA, and you require that both components are non-negative. And then there's a classical result that Robinson-Zove-Kotzius constraint qualification is violated for this formulation of the box constraints. But in our paper, we have checked that our AKKT regularity condition is still satisfied. Okay, and just some outlook, what we would like to do in the next time. First of all, it would be nice if the entire theory can be applied to problems with complementarity constraints in infinite dimensions. So in finite dimensions, there's already some work on the relation of AKKT conditions and MPCCs. And it would also be nice to generalize this constant rank constraint qualification we have seen for equality constraint, also for more general constraint sets in infinite dimensions. Okay, thank you for your attention, and maybe there are some questions.
Yeah, thank you very much, Gerd. I like the talk very much. Now I hear myself in a strange way, but I hope it's okay. Do we have some questions?
May I ask a couple of questions?
Yeah.
Thank you, Janos. I think we have some echo. If people who are not talking would mute their microphones, this would be helpful. Thank you. Thank you for the presentation. It was actually nice to see the stuff which was very popular in the mid-70s, probably, of the last century, being revived. Also the names, which are almost forgotten now, like Gould, things which I used to read many years ago. I'm wondering about the key concepts. So you are claiming that infinite dimensional case is essentially different from the finite dimensional one, and of course there are differences. I remember that even those people whom you mentioned during your presentation, they also used to produce some conditions in infinite dimensions, and in particular in Banach spaces, and I think they actually follow the philosophy that the Banach space setting is not much different from the finite dimension. At least this is what they tried to implement in their publications. So my first question is how this situation is different, the infinite dimensional situation, how much it is different. Of course, I understand that conditions like constant rank stuff cannot be easily extended to infinite dimensions. And you mentioned some more Penrose properties, which I'm absolutely not familiar with. And it would be nice to see how they actually look like in finite dimensions. This is the first question about the infinite dimensional generalizations. I have a more specific question. So you are introducing several types of regularity in terms of versions of Karush-Kuntaka conditions in infinite dimensions. And you definitely know that there exists certain just general regularity theory in terms of set-valued mappings, for instance. You mentioned Robinson regularity, you talked about constraint qualifications in the Robinson-Zove-Kurshich sense, which in finite dimensions reduce to Mangasarian Formulas, as you said. I think plenty of people just call it Mangasarian Formulas, despite it being infinite dimensional. And it is pretty well known by now that Mangasarian Formulas, it is just metric regularity of certain mappings. What can you say about your regularity conditions? How are they related to classical stuff, like metric regularity, which, as you already mentioned, can be too strong as a constraint qualification, but there are weaker conditions like subregularity, and in most cases, subregularity is sufficient. So please, if you could comment a little bit about the relationship of your regularity conditions and classical ones. Thank you. Back to you, Gerd.
Okay, so maybe to answer the first question, what is different in the infinite dimensional world? Yeah, first of all, of course, it's in infinite dimensions, you have several types of convergence. And often from boundedness, you only get weak convergence or weak star convergence. And in finite dimensions, you do not have this difference between strong and weak convergence. So this is a point which is very, very crucial in many places. And this is the very first, very obvious reason why infinite dimensions are more complicated. And the next version is that also this constraint set, if you think of this problem here in finite dimensions with convex sets C's and convex sets K's, then this is already harder than a standard nonlinear problem. Because for a standard problem, the set K here is a polyhedral cone, which makes life much more easier. You have the Farkas lemma for free, and this is also not the case here in infinite dimensions. And a third reason why it's harder in infinite dimensions is, I just think, no, I don't have a slide where I can point to this. Yeah, maybe for the linearization cone here. Yep. In finite dimensions, you typically write down this linearization cone by using the notion of active and inactive indices. Yeah, so you have here in the linearization cone, you need that the linearized equality constraints are satisfied, and you take the active inequality constraints, you linearize and require that they are non-positive. And now in infinite dimensions, you also do not have the notion of index sets. Yeah, and this, for example, the first difficulty to use somehow coordinate independent descriptions of the concepts you have in finite dimensions. In finite dimension, you always can use index sets, and if you try to generalize the ideas to infinite dimensions, you first have to get rid of the index sets. Yeah, the first in the linearization cone, for example. And the same happened for our constant rank constraint qualification. If I go back here, there you have this condition here, yeah, which is not really coordinate dependent, but it depends here on, yeah, depends on the finite dimensional structure, because in infinite dimensions you do not have a notion of rank of linear mappings which you can use here. So I hope this somehow answers your first question. Yeah.
Okay, thank you. But I believe what you mentioned, of course, it is straightforward, and it was known to all those people, Gould, Doyle, Kursich, etc. And they also talked about asymptotic, some kind of asymptotic conditions. In language of regularity of mappings, these are things pretty straightforward. Of course, you also mentioned this group of Brazilian researchers who indeed work specifically in finite dimensions, and I believe their things cannot be easily translated into infinite dimensions. But weak convergence, strong convergence, I think Gould and Toll had a nice paper. They also defined weak tangent cones. They didn't talk about Bouligan, because this name, actually people later realized that Bouligan had used all these things much, much earlier than that. But weak tangent cone, strong tangent cone, weak star convergence, people talked about all these things in the 70s, in mid-70s.
Yeah, but of course things are different, yeah, because weak convergence is not enough to pass through the limit somehow. Yes. Often you get a pairing of two weakly convergent sequences. Yeah, so things are quite...
That's why people are talking about asymptotic conditions. It is not easy to take limits. That's why people introduce asymptotic conditions.
Yeah.
Okay, thank you. What about regularity stuff?
Yes, this was your second question. Yeah, I think maybe it's best answered with the last with this picture here. Yeah, you have this Robinson-Souvre-Kotsos type condition, which is somehow metric regularity, and here you see that our constraint qualification is a little bit weaker. So I think this is what I can say, that this is somehow weaker than this Robinson type constraint qualification.
So,
and also this constant
this condition be, sorry for interrupting, of course, metric regularity is the strongest possible condition, which became popular many years ago, and hundreds of people are using it. And now it is pretty clear that for many things, sub-regularity is sufficient. Could any of your conditions be actually connected with sub-regularity?
We did not investigate this question. I can't answer that.
There have been a couple of publications by Joffe and I think Jiří Trata, who deduced the last line. Can you please share your slide instead of my photo? Your last line, ACQ and GCQ, they deduced, as far as I can remember, from metric sub-regularity. So metric sub-regularity is in between, and your conditions are in between. So it would be interesting really to understand the relationship of your regularity conditions with sub-regularity, for instance.
Okay, so we will have a look.
Thank you. Back to you.
Thanks. I think we have a question on the chat. Is the question from Younes Boutai. Would it be possible to say a word or two about the often event cones?
I think you mentioned this when you described the setting of your problem, that the constraints can be actually even cones. So the question probably is what you meant.
Yes. Yeah, if this is here I mean the set C and K which appear here on the right hand side are in many situations cones. Yes. So for example, if you have inequality constraint, then the K is just the negative orthant or something like this. Or for equality constraints, you just have the zero vector, which is also a cone. So in many situations, these sets are cones, but we do not need it here. So yeah, typically or often you do not have only convex sets, but cones, but we don't need this information here in our investigations.
Okay, maybe so one of my motivations for inviting you were because I see that these metric regularity people have their notion of regularity properties and you have yours, and you're working on actually solving a very similar problem, but with totally different methods or with totally different motivation. And that was why I thought it would be nice to bring this together. And I think what this talk also showed, I mean, maybe I'm a bit wrong and maybe Alex can correct me because he knows a bit more about that. Passing from regularity to sub-regularity is kind of getting rid of this interior point thing, of this total surge activity thing. And I mean, that's in a sense what you are also doing. You are getting rid of this necessity to have this, I always forget the name, but this condition what you started with, this classical condition where you really have either surge activity or an interior point. And you're doing that from a point of view of somebody who really wants to do an algorithm for a PDE. Other people are looking into structural questions. So I thought it would be very nice to bring these two worlds together. And then I have one question. If nobody else has a question, I have a question from a practical perspective. I mean, you have a weaker condition, and that means if I understand you right, every local minimum satisfies these conditions if you're in the proper space, have the proper problem, and so on. And then you have these Lagrange multipliers which don't have to converge. Is that a problem in practice, or does this give you freedom which you otherwise don't have?
Yeah, I think there you can have a look in our paper. We have a last section on SQP methods. And there one can check that such an SQP method always produces such an AKKT sequence. And if you, also for bad problems, so to say. And then if you have a bad problem, then the multiplier sequences which you get in your numerical computations are just unbounded. So somehow if you have a bad problem, you still get these AKKT sequences, but the multipliers which occur there are unbounded.
So that means that the SQP methods become applicable or become, well, you can treat them with this kind of theory, which you otherwise can't.
Yeah, but with the problem that in the end you get these unbounded multipliers, which is also not so nice in numerical computations.
Yeah, is there any workaround for that?
I don't know. Maybe try other spaces.
Yeah. Okay, do we have more questions?
I have a question. I have placed it in the chat.
So formulate it, Regina.
Yes. So thank you very much, Gerd, for your excellent talk. It was really beautiful. How does this picture change when you have a convex problem? Or
yeah,
if it changes at all?
Actually, you have still also for convex problems, you can still have some trouble, and because where I go, maybe I go here. Even for convex problems, you need here some constraint qualification, such that you get this equality here, which is crucial for deriving the KKT conditions. And similarly, for replacing the tension cone by the linearization cone, you also need some constraint qualification. So even if you have a convex problem, you do not get optimality conditions for free. You need some kind of a sum rule to get optimality conditions. And I think if you address this big picture here, that one, I think it roughly stays the same, independent of convexity.
I see.
What about the middle line in this picture? Are there still implications or equivalence?
Yes. No, I don't.
Okay.
No, I don't think you have equivalence here.
Mm-hmm. And okay. Can I just ask a very short question? And I apologize if it's I don't know, very trivial. When you define the lim sup and the outer and inner limits, even though when you are in infinite dimensions, can you use sequences instead of nets for defining those sets?
Yes, because at the end, for many results, we just use separability of the space or reflexivity.
I see.
And if you use nets, you always have the problem that weak star convergent nets might not be bounded. Yeah, you mean if you take here weak star convergence, okay, you can also do the same with nets, but then you end up with the problem that this net VK cannot be bound, might be unbounded. And I think that's also the reason why the limiting cone in infinite dimensions is defined with sequences and not with nets.
I see. It's defined in this way, and you use the strong convergence for X, I can see. Okay.
Yeah, here we have also a weak version.
I see. And in your conditions, in your asymptotic conditions, you never require that G of xk belongs to capital K, right? That's not a requirement for you.
Here. You mean here?
No,
yes.
In the strong asymptotic, in the asymptotic definition. In
yes.
The definition,
yeah.
You do not require G of xk belongs to K.
Yes. Yes.
You never require that. Okay.
Yes.
That's interesting.
Approximately.
Because typically you cannot ensure this in a numerical algorithm, for example.
I see, but if it would belong to xk, then the pairs gxk lambda k would belong to the graph of an enlargement of the normal cone of k.
Yes.
So in the limit, you go to the limit of the to the graph of the normal cone at the limit when rk tends to 0. So you could have used the property of the enlargements to deduce some boundedness of lambda k in that case.
No, it does not help. Lambda k might still be unbounded if such a condition is satisfied.
No, what I'm saying is that if you would have the fact that G of xk belongs to capital K, then the enlargement would be well defined, and you could use some properties of the enlargements, because G of x converges strongly to G of x bar.
Yeah, but the enlargements of the normal cone still contain the normal cone, and the normal cone itself is unbounded. So I do not see how this would help to obtain boundedness of lambda k.
No, you're right. The boundedness can only be obtained if G of x bar belongs to the interior of k, which is which simplifies, trivializes everything. Yes, you're right. Okay, thank you.
Okay, I think we are very nicely over time, so maybe we close the discussion for now. Yeah, thank you everybody for coming, and hope to see you soon again. Thank you, Gerd.
And yes, thank you to the speaker.
Thank you.
Interesting presentation.
Thank you for the invitation, Janos.
No problem. That was easy to do.
So I think the connection with Eastern Germany has been established, and let us keep it.
Yeah. Then all the best to Cottbus and see you next time.
Thank you.
Okay, thank
Bye.
you so much. See you.
Bye, everybody.
Bye-bye.
Bye.
Bye.
See you.
Bye. Thank you very much.
Thank you. Oh. Hi, Marian. Hi, Stefan. Good to see you here.
Another boy.
Okay. I hope things are going well in Europe. Okay, good. Okay, thank you everybody, and see you in a week. When again we have a presentation from Eastern Germany next week. Bye-bye.
Bye.
Bye.